Hello guys, welcome to my channel. In this lesson, we're going to learn how to find domains of algebraic expressions. Okay, let's go ahead and start with examples. Let me take the first example here. We're going to find the domain of 2x squared plus x minus 10. Alright, to do this, we just look at values of x that makes sense, or values of x that generate outputs. Okay, all right, so we know that this is a polynomial. All right, whenever you have a polynomial, you know that you can input any real number to get an output. So because of that, we'll say the domain here will be all real numbers. So let's write this down in words first. So we're going to say all real numbers, all real numbers. All right, but then there's a way you write the domains. Okay, you can write the domains in a set builder. You can write the domain in a interval form and so on, and algebraic form and so on. All right, so again, to represent real numbers, we use this special character R. Okay, so that's what real numbers represent. Okay, so we can say that the domain will be x such that x is all real numbers. Okay, so this here means a member of. Okay, so you're just saying that x is an element of. Okay, sometimes you say an element of, an element. All right, okay, these are just notations. All right, okay, so you can write the domain like this. You can write this in interval form. So this one here is called the set builder form. Set builder of notation. Okay, set builder form, or you can just simply say set builder notation. Let's write set builder notation. What about if I wanted to write in a different way? Let's say interval notation. So for the interval notation, that's when you use like brackets. Okay, so because the set of real numbers here, this is number line, you have it all the way from 0 going to the left, you approach negative infinity, and to the right you approach positive infinity. So we would use the open brackets like that. So this will represent the set of all real numbers. Okay, so this is an interval notation. Notation. And if you wanted to write that like maybe as an inequality, you just write x here. X is greater than negative infinity and less than positive infinity, because infinity is not a real number. Okay, we always say that. So you have to notice that infinity is not a real number because you don't know what that is. So usually you just write your notation. This is like inequality notation. I hope this is helpful enough. Let's go ahead and do another example. Okay, I'll do that in a different column. I just separate. So let's take another example. We're going to find the domain of this expression right here, x minus 2. All right, so we know that this is a radical. This is a radical expression, yes, because of the square root. Okay, and then we also know what complex numbers are, that it's possible to have a complex number when you have the radicand is negative. So if the radicand is negative, we get complex numbers. So, and then we're looking at domains to be a set of numbers that are defined in the real space. All right. So because of that, we are going to be very careful here to define the domain of this expression with the square root of x minus 2. So one way to do this is you do not want the denominator, you do not want the radicand, not the denominator, the radicand to be negative, because if that's negative, the whole thing becomes complex. So you do not want whatever is in the radical sign to be negative. All right. For example, like if you end up with -1, that's what you call the imaginary unit I, right? If you end up with maybe -4, maybe -4, you know that that's going to be like the square root of 4, which is 2, right? But because it's negative, the radicand is negative. It'll be 2i. Okay, so you do not want complex numbers. So because of that, to avoid that, we say, okay, you know the domain will be such that whatever the radicand is must be greater or equal to 0. So this is the trick or the strategy to find the domains of expressions involving square roots or radicand like that. Okay, so you want x minus 2 to be greater than or equal to 0. So when you do that, you solve the inequality. You add 2 on both sides. So I'm going to add 2 to both sides of this uh, inequality, and then I get x will be greater or equal to 2. So you want x to be greater than or equal to 2. So this will be the domain of this function right here, of this algebraic expression right here. So which means the domain here will be in set builder form x such that x is greater than or equal to 2. What that means is that uh, when you input numbers that are exactly number that's exactly 2 or more, or to the right of 2, you would get real numbers, because that's what you're looking for. So because you know all the numbers on the x-axis are real numbers, and that's where you want your domains to be, so that when you impute these real numbers, you get an output right in the real space. So because we're not working with in the complex space. So this is how you can write this as a set builder. So if I wanted to write this as an interval, it would be square bracket 2 all the way to positive infinity. So this is how you write the interval notation for the domain. Interval notation. And this one is set builder. Set builder notation. And if you wanted to like represent this as an inequality, it'll be x is greater than or equal to 2 and less than positive infinity. So these are the ways in which you can write the domain. So the domain will be that. Okay, this is inequality. All right, so we can do more. Let's go ahead and just try another one. Let's take example 3 here, where we have 2x divided by x minus 2. All right, so here we have a quotient, okay? We have a quotient. It's a fractional expression here. And then when you have fractional expressions, you're trying to be very careful with the denominator, okay? So your goal is to work on the denominator such that you know what happens when you have a 0 as denominators. So you have an undefined expression, so it becomes undefined, and you do not want that. You do not want the denominator to be 0. Okay, if you do not want the denominator to be 0, what else do you want the denominator to be? So this is what you can do. So the trick here is you set the denominator not equal to 0. I like to do that. So I would like, okay, I'm going to go ahead and say I do not want the denominator to equal 0. Okay, this is one strategy that's helpful. So because of that, it means that you do not want the denominator to be what? 0 means that x minus 2 is not equal to 0, meaning that you can add 2 on both sides, so that you do not want the denominator to be equal to, you do not want the x value of the denominator to be equal to 2. So what I did here was just add 2 on both sides. All right, so you have x is not equal to 2, right? So when I cross this out, I get x is not equal to 2. So if x is not equal to 2, what that means to me is that on the number line, because x represents all real numbers, remember that. So x means all real numbers. Okay, cool. All right, so now we know that 2 is to the left of 0, right? So we have 2 is to the left of 0, okay? I mean to the right of 0, sorry about this. So 2 is to the right of 0, so I'm going to have 2 here, okay? So now I do not want my denominator to be 0. So what I'm going to do here is I'm going to create an open ring for 2 because I do not want my denominator to equal 0. So that means I need to avoid and stay away from 2 because if I impute 2 exactly, it will give the denominator equal to 0, right? And then the numerator, of course, if I impute 2 there, it's not a problem. So, okay, so what I'm doing here is I am looking at numbers that are different than 2, right? So which means numbers to the left of 2 and also numbers to the right of 2. So in this case now your domain is going to be like, you're going to need a combination of a set of numbers that do not include 2. So here I know that I have a negative infinity here and I have a positive infinity here. Okay, to the left of 2 I know that I have negative, I can approach negative infinity. To the right of 2, I can approach positive infinity. So because of that, my domain will be in 2 sections. So it will be a combination of negative infinity and 2 here, open brackets. Then you introduce this symbol here called union. So like that, okay? And then you have 2 comma positive infinity. So this is how you write your domain in this case, all right? So you do not want that. So, but if I just want to make something up as a set builder, or I can represent that as x is a real number such that x is not equal to 2. This is good. All right, so let's try another example here. Let's take, for example, uh, this problem here. X plus 3 divided by x squared minus 4. Now, for this problem here, I just need to set the denominator not equal to 0 as well, because I do not want the denominator to end up being 0. Otherwise, I do not get an output. All right, so what I'm going to do here is to also, like I said, the trick here is just to focus on the denominator, right? So, okay, so I'm focusing on the denominator because the numerator is all good. The numerator is a polynomial, so I do not need to worry about the numerator. Okay, so now I am going to make sure I'm going to say x squared minus 4 cannot be equal to 0. All right, so what I can do here is I try to factor this result here, or I can set that equal to 0 and directly solve using square root method. Yes, so meaning I can just do x to the 4th. I'll add 4 to both sides and I'll get not equal to 4. Then I'll take square roots of both sides and I have my plus and minus sign on it so I can get 2 values for x. Of course, you see this is like a quadratic expression. Or I can just factor because this looks like the difference of 2 squares. So it will be x squared minus 2 squared. I do not want that to equal 0. So meaning that I can factor this expression as a difference of 2 squares. So it becomes x minus 2 and what? X plus 2 cannot equal 0. What that tells me is that I'll end up having x minus 2 is not equal to 0. X plus 2 is not equal to 0. This is how I want my domain to be. So which means I'm now going to avoid 2 numbers, which means I do not want my denominator to be x, to have x equal 2, and my denominator cannot be x negative 2. All right, so I am going to take my eraser and delete some of what we've done so I can have enough room to show you more examples. Just be patient a little bit and I will create more space for us to work with. All right, so this is a trick that I use and it doesn't fail me. So I use this trick all the time. You're going to be learning how to operate functions or find the domains of functions This is the exact same thing that you do. So, okay, so I am going to go ahead and move over to this space where I can show you more. So since I do not want x to equal 2 or x to equal -2, it means that my domain will be like this. Let me show you what I'm trying to do here. So there are two numbers that I need to avoid. I need to avoid x being -2. I also need to avoid x being +2. So then that means I'm going to have a ring here, an open ring here, and another open ring there where I have to avoid these numbers. So which means I can work with numbers in this boundary, and I can also work with numbers moving in this boundary like that, okay? This is what I have. So you can see that now the number line has been partitioned into three different intervals. So the first interval here, of course, you know, you approach -infinity to the left and you approach +infinity to the right. So my intervals now will be 3. So that which will be contains, which will include -infinity to what? And -2 here. And then I'm going to do union. So then in between -2 and 2, I have -2, comma 2. And I have to have another union, and I have 2 toward +infinity. All right. So these are the domain. This will be the domain of this expression here for number 4. All right. Okay, this will be about it. So let's look at one more example. Let's say example 5. This time I'm differentiate using a green color. So I have x plus 3 divided by x squared plus x minus 6. Again, the numerator here is not a problem. It's a polynomial, so we're good with that. Okay, so but for the denominator here, you can see we have a polynomial here, and then you know polynomials can have zeros. They have zeros, yes, in the real space. So what I'm going to do here is I will set the denominator again not equal to 0 because I do not want that to happen. Okay, so doing that means that x squared plus x minus 6, we do not want that to equal 0 because if it happens, we have an expression that is undefined. And then you want your domain to be defined in the real space. Okay, so from here, I am going to think about how I can factor or how I can solve this equation right here if it was like a quadratic equation. So how do I solve that? I can use factoring for this, yes, which factors into x minus 2 and x plus 3, and we don't want that to be equal to 0. So this can be factored into that. I hope you watched my previous videos on how you can factor this polynomial here, or this quadratic equation, quadratic here, okay, quadratic expression. So once you factor that, then it means you do not want x minus 2 to equal 0, or you do not want x plus 3 to equal 0. From your factory, you can do this. So then you can add 2 on both sides. You do not, that means you do not want x to equal 2, or you do not want x to equal -3. So from this result, again, if you draw your number line, it is easy to see that you are going to not include 2 here and not include -3. So because of that, you just kind of draw open rings around those numbers that you're avoiding. And this set of numbers will be good. And the set of numbers to the right from 2 will be good. Set of numbers from left to from -3 all the way to the left will be good. So now we have our domain. So the domain will be the set of numbers from -infinity and set of numbers -infinity 3. Okay, we put union -3 and 2, and then one more union 2. Again, we have +infinity right here, comma +infinity. So this is how you will represent your domain. I hope this lesson is a little helpful, and come back to watch more videos, and I will see you in the next video. Thank you very much.